All right, day 44. Let's talk about something we see every day. How does your phone's autocomplete seem to, well, read your mind? Or how does a translation app get the little details of a sentence just right? Well, the secret is a special kind of neural network, one that has a memory. Today, we're going to break down recurrent neural networks.
So think about an idiom like this. The meaning doesn't come from the individual words, right? Under and whether on their own don't mean sick. It's the sequence, the order that matters. And for a machine, figuring out that kind of sequential context, that's a really tough problem. And that's exactly what we're going to tackle. By the end of our time here, you'll get the core idea of how a neural network can actually build a memory to understand sequences, things where order and context are everything. Okay, so let's start with the basic problem. A standard neural network, well, it has a bit of amnesia. It treats every single input as a brand new event, completely separate from whatever it just saw. There's no memory. A recurrent neural network, or RNN, is built to fix this. It's designed with the assumption that inputs are connected, that they're part of a series. It actually carries information from one step to the next. And that is the key problem they solve, giving networks a memory. And the way it does this is actually pretty intuitive. It all comes down to a feedback loop. When an RNN processes an input, it doesn't just produce an output, it also feeds a piece of information back to itself. So for the next input, it has some context from the previous one. It's basically looking at the new information while also remembering what it just saw. Here's the best way to think about it. When you read a sentence, you're not just looking at one word at a time. You're building up a mental summary, a kind of running gist of what's going on. An RNN does the exact same thing. And that gist, that internal memory that gets updated with every new piece of information, that's what we call the network's hidden state. Okay, so this simple feedback loop sounds great, and it is for short sequences. But, what happens when the really important context wasn't in the last word, but maybe 10 sentences ago? Let's look at a classic example. To fill in that blank correctly, the network has to remember one key fact. Alice is allergic to nuts. That's the crucial context. But what if there were a bunch of other sentences in between? That's where things get tricky. This is where that simple memory starts to fail. It's kind of like a game of telephone. The further the message travels, the more it fades or gets distorted. For simple RNN, that crucial nuts information from the beginning gets weaker and weaker with every new word it processes. By the time it reaches the blank space, that original memory might have just vanished. And technically, this is what we call the vanishing gradient problem. The signal from the past just gets too weak to be useful. So, if a simple memory fades over time, what's the solution? Well, we need a smarter way to manage that memory. We need something like intelligent gates. And that brings us to one of the most important ideas in this space, the long short-term memory network, or LSTM. It's a special kind of RNN, but with a much more sophisticated internal structure. The big idea here is that it uses a system of gates to very carefully control what goes into its memory, what stays there, and what gets kicked out. So let's break down how these gates actually work. You've got three main ones. First, there's the forget gate. Its job is to look at the old memory and decide what's no longer relevant, what to just throw away. Then you have the input gate. It looks at the new information coming in and decides what's actually important enough to save. And finally, the output gate. It takes the current memory and decides what part of it is useful for the task at hand right now. And this whole system of gates, this is the solution to that fading memory problem. Going back to our Alice example, an LSTM can learn to use its input gate to recognize that allergic to nuts is super important and must be stored. Then, its forget gate can learn to ignore less important details along the way, so that crucial piece of context survives over a really long sequence. Now, LSTMs are incredibly powerful, but they are also a bit complex. So, a slightly simpler version was developed called the Gated Recurrent Unit, or GRU. A GRU basically combines the forget and input gates into a single update gate. It's more efficient, a little faster, but maybe not as expressive for really complex tasks. Think of it like this. An LSTM is a powerful, complex tool, while a GRU is a more streamlined, faster version. Both are useful, just for slightly different jobs. All right, so that's the core theory. But where do we actually use these things? Let's talk about some real-world applications. You'll find these networks pretty much everywhere that sequence matters. For machine translation, they help keep track of grammar and context from one language to another. For sentiment analysis, they can read through a whole product review and understand if the tone is getting better or worse. They're also crucial for speech recognition, processing sound as a sequence, and even for predicting things like stock prices or the weather.
But maybe the most common example is right in your pocket. When your phone's keyboard suggests the next word, that's an RNN-style model at work. It's looking at the sequence of words you just typed and making an educated guess about what's coming next. It's pure sequence prediction. So if you remember one thing, make it this. RNNs gave neural networks a memory, and advanced versions like LSTMs and GRUs made that memory intelligent. And that leaves us with a question to think about. If a machine can learn what's important enough to remember and what's safe to forget, what does that really say about its ability to understand?